'cause I don't recognize you anymore. Once sweet and caring, now cold and calculated. You can't be trusted. You want the world for your own. You want maximum profit. I can't afford to stay, so get out of my way. Smoking down the track, I never looking back. You can't be with me anymore. You can't be with me. Once I will let you in, but now I let you go. I can't afford to stay, so get out of my way. Smoking down the track and never looking back. You can't be with me anymore. You can't be with me. Yeah. Once I will let you in, but now I let you go.
Okay. Hello? This thing on? I think it is. Welcome everybody. I'm here. I was getting a lot of things ready. That way we could get maybe some huge milestones today on my Rust development process. Let's see. Last time I was having some issues. Trying to get my timer to actually be time sensitive. You know, it would say I put a 200 millisecond timer using this framework rather than some hardware timers, and the 200 millisecond would be short by 150 millisecond. I see that there's an ad break in progress, so I'm just gonna kind of filibuster a little bit just in case somebody gets an ad and isn't able to see any of this. But those of you that might be listening to the VOD, disregard this because there's only 10 more seconds left of my filibustering, because I could really just talk on and on and on and really have no agenda. And by the time that I finish this sentence, the ad break is done, and welcome back. So anyways, yeah, timers. Last time, timers were not accurate with their time. I did some research, talked to some people using the embedded Discord that I've come across, as well as just reading documentation. And I think the reason, and I'm more confident that this is the reason, I think the reason we weren't getting our timing is because behind the scenes, we needed to pick a tick rate for our clock that was divisible, that our delay time rather is a divisible number. So what I mean by that is we have our big number, right? Our big clock number, and we need to divide that a number of times in order to generate this specified time delay amount, and in our case it was 200 milliseconds. Now I think by default this example runs at a rate that's like 360 kilohertz, some number that's not quite a even distributor for 200 millisecond. Granted, okay, I said 360. There's some other numbers in there. It's not an even number, I promise. At least to 200 milliseconds, I would think it's not even. And I think we can explore that a little bit. So one thing I'm gonna do is probably recheck out this embassy library because I saw that there were some updates that happened to the repo, and I kind of want to pull the latest. So I'm gonna go ahead and jump into the dev scene now and show how I kind of get my stuff. I usually come into the code base and copy this HTTP, and then I come into the folder that I want to do it into, and then I do Control L and CMD to actually open a command prompt really quick and easy. And then I hit them with the nice git clone, and then I paste my HTTP link there, and it go ahead and produces my embassy local clone. So we're gonna be maybe doing more development into this directory today because I think it might be better to start inside of an example just to make sure we've solidified how this thing works, since we've been having so much trouble understanding the language on top of the framework. Framework exists, but I also am learning Rust at the same time. It's 2-in-1, which is not a traditional way, I'd say, to learn this stuff, but we can do it. Okay. You know what? I think I need to open it in one directory inward, because I want it to link together everything for this example. So I'm just gonna go ahead and grab the exact folder, the examples folder with STM32, since that's what I use, and open my terminal in here, or my code rather in here. Go this route. You could just ignore that for now. I usually don't want to get rid of any pop-ups unless I know exactly what should happen. But yeah, where are we at? So we have this blinky.rs. This is what the program produces by itself. And so if I alter, if I keep this how it is, basically this will start blinking the LED. So I'm gonna do STM32. No, wait. We're gonna do partial run. Blinky. Oh, I need to update one of these. I just realized, because it overwrote what I had there originally. I think it's in here. So when you check it out from scratch, this becomes 85 when this should be 75, and this should also be, I believe, XT. Oh wait. It should be ZI. Replace ZI. Replace C. Okay. And then that's fine for this page. What we want is on a different page. What we want is in here. We want to change this one to be, I think I can do a probe rs -s list. No, not that. Okay, what if it was -chip -list? I did chip. Just help. Unexpected argument, chip. I don't remember the exact command. Instead, what we're gonna do is just go up a bunch of times so we can find the exact. Oh, actually, no, that's not gonna be there. Never mind. We can just start by removing this. We can just start by removing this. Oh, why am I not selected in? Huh. Seems a little glitched. Okay, there we go. 0.75. We're gonna keep it like this for now. So that way, oh, I think that's fine. Yeah. So that way, if I go ahead and do cargo run dash bin dash dash, oh, sorry, Blinky. This is going to compile it. And it's going to give me an error saying that it doesn't know the chip. And it's going to give me the options of other chips. And then we'll choose one of those. I just realized, so you could probably zoom this in so it's a little bit easier to see on stream. Is that good enough? Start with that. That seems clear enough to me. Okay. All right. We have a bunch of different options. What we want is this ZIT. ZITXQ actually. All right, run the same thing. And then it gives us the error saying that's missing our serial port. So we're going to go ahead and edit this to have the probe. I think that's what this command is. Where we put our ST link. We went over this on last stream, but we have to do it again since we cloned the repo. And then that should do everything for us. Sweet. So if you look here, nothing's happening. Why is nothing happening? Ooh, that's a problem. Let's see why that's a problem. Maybe this is not the full thing. That could be it. Like maybe I need a little bit more wording in it, which is fine. All that means is we got to open up the documentation for him to see and just quickly find it. I think it's this documentation. No. This is that number, by the way. 32,768 hertz. That is that default time. I feel like I've never been on this page. No, I have. Never mind. I have been on this page. It's just throwing me off. Just getting a little bit confuzzled. Maybe I haven't read this in a while, so it actually looks less familiar to me. We want a different kind of docs. API reference, I guess. Yeah. And then we'll go down to our chip, which this is what the name's going to be. 75ZI. Oh, okay. That actually is the name of it. A little bit awkward there. I'm not really sure why it's not blinking. Oh, I see. It's not the actual... The example had it putting it on a different pin than what we use. It had PH7. We use PC7. There we go. Now if you look, it's blinking. Right? It's blinking. Going back to it. What we want to do is put this on a different pin so we can see how it currently sits. Okay, just a recap from a few streams ago. Oh, okay, yeah, from a few streams ago where we were able to see that it doesn't actually meet the desired frequency. So PC7 is what it's at right now. To make it be on the pins that we want to put it on D0, which is D0. If we search for D0, is gonna be, oops, it's going to be, that's PD0. D0, oh, there it is. D0 is PG8, so we need to change our code to be on PG8. Replace G over replace 8. All right, same thing, but you want to see the LED blink, you'll instead see it on the waveform. Okay, if we have our waveform here, we can measure it and see that it's, at least today, it's going a little bit over. Now we got one tip that perchance it can't divide into it because of that default clock. Another thing is it's based off of the internal oscillator, which has a plus or minus 5% error. So there was a theory that maybe it's because of my hardware, but I feel like off of my previous experience, I got better than 500 milliseconds of error. That seems really bad. Sorry, not milliseconds, 500 microseconds. So we're gonna see. We're gonna see if we can tweak this thing to be a little bit better. So first we're gonna start with looking at our cargo and going to this section here where it has a set tick hertz rate for the time. Now, if we do some math, we have a 200 millisecond. We have a 200 millisecond time. Delay, rather. And if we convert that into frequency, hold on, I'm just trying to see if I can make this a little bit easier to look at. Looks like this might be it. So we have 200 milliseconds, right? I'm also trying to choose a different song. This song seems okay. 200 millisecond. Okay. We're gonna see that this is a 5 hertz task, meaning it happens 5 times per second. Now, this clock timer ticks at a rate of 32,068 hertz. Okay, 0.2 divided by 1 is 5 hertz. So 5 does not divide 32, 70, 68 easily, which is why we're getting maybe this inconsistency error. We're not getting the exact amount. So what we can do instead is go to this repo for embassy time, the documentation for embassy time. Would it be here? Documentation. No. It's in here. We're gonna open this in a new tab. And we're gonna go to embassy time. And then we're gonna go to another section where they talk about tick rates. And we're gonna find one that is divisible by 5. So this one's divisible by 5. They defaulted to this one. We're gonna do 1 megahertz. We're gonna see what happens when we set it to 1 megahertz. So we can come here and replace this as 1_000_000 to call the flag or the feature for this clock rate, 1 megahertz. Because 1 megahertz or 1 million is divisible by 5, which 5 is 200 millisecond hertz. Or not millisecond hertz, just milliseconds. But all right, so we got that. We then need to recompile and flash our code. And then when that's done, we're going to jump back over to the waveform. Okay, going back into the waveform, and we're going to scan this. And we're going to see that that did absolutely nothing. We're going to see that it doesn't matter. It doesn't matter. Look at that. 201, 200, 201, 192. That's disappointing. I don't know what to say to that one. Granted, there's some time that is taken every time you send stuff over this log, right? That's a context switch that takes some overhead. All right, so you're not You may not get exactly 200, but going back to this. Oh boy. Going back to this. I'm seeing it jumps up for 200. Then it writes something. It jumps back down. It's down pulse 192 here. 192. Granted, this could be a problem with how the screen was updating. Yeah, I think it was. Never mind. My data was overwriting the previous data. So ignore that 192. That's inaccurate. But yeah, still not fixed. Okay, so we got a few different recommendations. If I go to my conversation that I had with the person who made Embassy, it's in my Discord. They listed a few different things. Just going back to it. Okay. So they said try clogging from the hardware external oscillator. I don't think I can actually do that with the current setup because I need to install it myself. So then I go to a different section where it says for more accuracy, I can use the ticker option instead of timer. And then I might be able to have a better time. So let's see how we can do that. I'm gonna go ahead and pause that. And we're going to import, alongside timer, we're going to import what is this, a struct? An object? It's going to be called ticker. Let's see, yeah, this is a struct. And this struct, you give it an instant and a duration. Duration for us would be the 200 millisecond. All right. Our instant, we only need to see what that's about. So if we comment this out, and instead of timer, we put ticker, let the auto complete kind of give us some options. It looks like we don't have too many. Looks like we don't have too much. Oh, I see. We need to do the scope operator and then see what functions we can call. So should we do every 200 milliseconds? I'm not so sure. I think what we should do though is open up the documentation for this ticker. Or we can look at the code to see if there's any clues here. Okay, wait, create a new ticker that ticks at the specified duration interval. Reset the ticker back to its original state. This causes the ticker to go back to 0, even if the current tick isn't over yet. Waits for next tick. Okay. So it looks like you would do a busy while loop kind of thing with this. This fragment will not call. Oh, here we go. Asynchronous stream that yields every duration indefinitely. Oh, but that's duration. We did this ticker every duration. Okay, so we could do this tick where we're toggling its level. So how about we do it like this? We create a ticker object, right? Let mute ticker is equal to ticker every, and then the duration, I think we need to pass in duration. Yep. Oops. From milliseconds, and then we pass in 200. Thank goodness for autocomplete, because I would have had to look at the documentation a lot more. But let's double check to make sure. Yep, that's how they did it. So now what we have to do is every 200 milliseconds this tick is going to happen. All right. We are going to change the logic just slightly, just so slightly, to be a if. How about we make it like this? Is there a toggle? LED toggle? There's a toggle. Okay, we're gonna ignore the on-off stuff right now. We're gonna ignore on-off. We're gonna ignore low and high. We're simply just gonna run toggle. And I think we need it to wait. What do we got here? Ticker, next, await. We go ticker, next, await. So if I'm not mistaken, this code should enter the loop, toggle an LED, and then wait here, like a busy while you'd see in embedded C. So let's go ahead and try and compile this. Ooh, okay. Oh, that's okay. We're just getting a warning saying we're not using timer, and that we have some DFT timestamp warning, but it doesn't look like it should affect it. This could be interesting. This looks like this is what the clocks are doing to initialize themselves, but we'll not worry about that at the moment. We'll just see how the waveform looks. I hit scan. Ooh. Ooh. Oh, buddy. It looks like this is the same, if not worse. If not worse. 198.5, 198. That is a bummer. Okay. So that didn't work. That's two solutions that didn't fix the problem. What I do really wish I could do is remove all variables altogether and just make it where I'm doing hardware. Just pure hardware. Pure registers. Nothing more, nothing less. Now I wonder if I change the speed at all, if that's gonna matter. Just want to quickly look if they have anything to note about the speed. I mean, very high speed does sound nice. I feel like that shouldn't matter though. If I change to very high speed, let's see. Very high, because I'm pretty sure I did this. I did this last time. Yeah, 198. Still there. No worries. At least we learned how to use their tick. You know, the tick counter. That's handy. We don't need that. Very high doesn't matter, just using more power. We're gonna change this back to medium. Just to keep it simple. The issue is embassy time is based on a hardware timer. So it's said to believe that this internal clock is actually, it's swaying, you know? It's not perfect. Maybe there's a clue here. Maybe there's a clue here. I'm gonna turn down music a little bit. I'm under the impression that maybe it was too loud. Okay, so maybe there's a clue in this debug statement. Since it's talking about clocks. RCC is our clock register. Audio clock, none. H clock 1. We're looking at 4 million hertz. 4 megahertz, yeah. H clock 2, 4 megahertz. H clock 3, 4 megahertz. HSE none. HSI none. HSI 48, some megahertz. HSI 8 divided by 2 none. LC none. LSI none. So I know a lot of these values because these actually correlate to the different stages in the clock configuration. If I were to pull up one tool I have, the Cube MX tool from STM, you are able to create kind of like a clock tree. I just open up some random example. I could probably find a LED blink actually for this. Maybe we can find that and just load that on. This would validate if you're able to get that 200 millisecond or not, and if it's hardware, if it's actually just my the code. Let's see. I didn't think to do this. This would be the most safe way. Glio U5. Well, we'll worry about updates later, I guess. U5 75. Okay, so that's our board. Now it's giving us a bunch of examples. If we go to timer, I believe, infinite LED toggling. This could probably be fine. Just want to make sure there's not a better one. What is time base? Real-time clock alarm, wake up, real-time. Okay. Hold on. Timer 7. When the user presses the user button, the tick increments is suspended. Okay, we don't want that. Let's go to the T's. If there's any other time. Okay, hold on. Time input capture at the beginning of the main program. Input capture mode. I don't think we're doing input capture. We're doing an output capture. Okay, yeah, this one sets a pin. 250 millisecond. Okay, well, this is fine. Turns on if examples. Okay, yeah, let's just start with this one. This one will work. This will show us the clock that needs to be set up in order to get some of these different counts. 160 megahertz is more than enough resolution. But here's the clock screen I was talking about. So the values on this terminal, like audio clock, H clock 1, H clock 2, they match the same names as what's on this sheet here. HSI 1 will be on here as well. So they saw H clock 1. H clock 1, I believe, is... Oh, I thought it was on one of these edges. Here's H clock 1. H clock 1. Oh, okay, hold on. But you see H clock right here. It could be referring to this H clock right there. H clock 1, H clock 2, H clock 3, H clock... Hold on. HSE. H clock 1, 2, 3. There's only one H clock on this page. So I'm not sure what it's referring to the other two. But regardless, they all have the same value in my example that I ran in the code or in the console. So it couldn't be much different than... They're all the same value, so it has to be corresponding using one of those values to fill in this data field. Oh shoot, my bad, Phil. My bad, Phil. This isn't Rust, you're right. Oh shoot, my bad, my bad. Dang it. Yeah, darn, it looks like I'm just gonna have to keep riding. Just not knowing what to do. I'm waiting for my Zerg door campers to come in. Maybe the stream's broken. This is definitely Rust. Just close your eyes and it definitely will be Rust. You know me. I'm so excited for Rust, but instead just some gay nerd stream. Yeah, I know. But again, if you close your eyes, it is just Rust. It is just Rust. Oh, what is this? This is new. Oh, wait, that's not new. Kind of just going through these menus. Memory management. That's kind of neat. I don't know why I've never looked at this screen. This is a cool tool. You could be able to do this stuff. Physical memory. Huh. So even though it's separated like this, you just treat it like RAM and flash. Separated like that. I didn't even consider that, but I like that. Oh, whoa, look at that footprint. Whoa, 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 whoa. Dang. These are different options. Detailed, pin detail. Basic would probably be the one I would ever use. We're using KiCad. Subscribe to T. That's right. Make sure you use those Twitch Primes. Ooh, pinned by Phil. That's a good idea. That's a good idea. Subscribe to T Rich if you want more Rust content. Take that with what you want. Rust can mean a lot of things. Can mean a lot of things. I'm gonna generate code. These peripherals still have not configured, blah, 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 blah. Yes, generate the code because this example, it should just work. Examples are supposed to just work right out the box. So if I come into here, allegedly, I can just run make. Let's see if that's true. Make. Tisk. We need to go into... Yeah, wait, what? I could not find file special. Like, why would you even generate... Why would it have a setting to generate a make file, but not actually generate working code? It's supposed to just work right out the bat. That's kind of dumb. That's actually very dumb. README HTML. This is just what was on that page. Let's open this really quick in code. Let's go to terminal. So if I run make, it doesn't know what to do. No such file. Jeez. How about I go into the make file and see what it's looking for. I think I have a clue. I think I need to either put a flag or I need to uncomment something. It's not looking like that. It's saying main can't find. Can't find this. No, wait, can't find this. Where'd that even be? I think that's funny. I really do. You got this HAL here. This example of HAL, at least. Doesn't even give you the code you need. But I bet you if I ran... if I ran this in their IDE, it'll work just fine. So let's do that for giggles. So if I change this to be a Cube IDE project and I generate it, yeah, that's fine. If I generate it, I bet you it's just gonna work first try because vendor lock-in, right? Vendors love it when you like their methods. So that way you keep using their stuff and then you get super pigeonholed. Okay, open up another one of their tools, which is just an Eclipse skinned IDE. Sorry, STM skinned Eclipse IDE. Wait for it to load. Hopefully it doesn't need to spawn some kind of update. That would not be fun. All right. As you can see, super big text. Okay, it imported our thing. If I go to... Actually, if I just click right onto this and click build, we can see down here, it's building. Oh, look at that. It just works. It just works because STM would love you to just use their stuff. That's annoying. Anyways, I'm going to quickly... Oh, hold on. I got to make sure I'm not holding the port open, which I am. Lol. Okay, back into here. This is like the official way to do STM stuff. If you're just going to do it how they intend, you use all their tools. It works. It's just not pretty in my opinion. And you're kind of pigeonholing yourself. You get too comfortable with this. So I think I just need to right click onto this and do run as. Yeah, this is okay. This version, no, oh wait, provides a newer version. No, we don't want a new version. Fail to start GDB server? Why is that? Okay, well, looks like we were forced into updating our device. So I'm just gonna update my device real quick. Huh? What is this? Sure. Maybe this update's pretty fresh. There's always that possibility. You can see it's blinking. It's doing a big blinky thingy. The blinky thingy is what says it's programming. Alright, cool. Whatever. Now that that's out of the way, let's try that again. Let's do build. No, wait, not build. I mean, I'm used to hitting like debug or run at the top. Oh, it's changing to debugger view. Download verified successfully. Okay. Apparently it downloaded, but I don't actually see anything. PC7 is our LED. But if you look at the camera, this is not blinking. It's not doing the blinky thingy. This example is supposed to do it all for you. While loop's empty. This house starts compare 1, 2, 3, and 4. Output compare. System clock. I know this is such a different page to be looking at. I'm just trying to quickly put this on. What actually keeps this from ending? I mean, you got infinite while, so I guess it'll always be here. Yeah, I guess it'd always be there. What the heck? You can't zoom in on this? I'm over here trying to zoom in. It actually won't let you zoom in. That is so silly. Oh, and he hit resume. Okay. That's why I wasn't blinking before. That makes more sense. Seriously though, what? I should be able to zoom in. Maybe it's view, file, edit. That's a viewer. Perspective. Nope. 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 None of this. None of this. Come on. This can't be the only way to look at it. I swear Control plus doesn't actually zoom it in. Shift plus just writes it to the code for some reason. What I'm trying to figure out is why the LED is going on. Okay, whatever. Maybe it's going super fast. Maybe that's it. So let's go ahead and change LED 1 to BPC8, or what did we have here? We had PG8. Okay, we want PG8, which should involve calling a different function. This is just initializing it. LED on. This just turns it on. Okay. Oh, but what is actually our output? Do we even have an output to this? I don't think we do. I think we just have some code that allegedly does some output compares. Time channel 1 selected. So you pass in a timer and then a channel. You do some comparing. And then you enable an output. And you say, okay. Do I need to pin? Do I need to look at a particular pin? Let's go back to this. Maybe this will explain it better. Maybe not that just quite. What if we go? Okay, maybe this will work. Never mind. Timers. Let's see what's going on. Timer 1. Output compared channel 1. If we go to the pinouts. Oh, I see. We're supposed to pin out. We're supposed to hook up our oscope to these pins to see how accurate it is. Okay, let's do that. PE9, PE11, 13, and 14. So let's see what those are. Oh, look at that. It's right here. PE11 and 14 and 13. 13, 14, 11, and 9. Where's 9? Is there a 9 on here? B9 right here. 11, 14, 13. Okay. So I'm going to go ahead and do full screen cam on the circuit. We're going to hook up a little bit more wires. 9 is D6. Fortunately, the text is super tiny, so it's not going to show up on the camera, but just know that I'm plugging it into what I'm saying. So I plugged one into D6. We're going to go D9 or D5 next. And then we're going to go D4. And then D. D5. Oh, sorry, D3. D3. 9 for PE9. Or sorry, D6 for PE9, D5 for PE11, D4 for PF14, and D3 for PE13. Just like they wanted us to. We're gonna go to the waveform and add a few more signals. 1, 2, 3, and run this thing. Just to see nothing happen. Perhaps our program is frozen. It needs to be... We need to hit run on it again. Nope. It's live. Not actually doing anything. So that's not really cool. Maybe I need to reset it. Ah, okay. I did need to reset it. So this program works off of you hitting the reset button. Are we gonna do repeated? No, wait. Okay, stop. There we go. Okay. So one thing I noticed is that, well, apparently one of the pins isn't even doing anything. Not sure what that's about. Let's do shift. What does the example say? What's the delay on I don't even know. I don't know what to call it. P4? Maybe? It's not even activating. Nine, 11, 13, 14. 9, 11, 13. Oh, okay. Wait, no. 9, 11, 14, 13. Yeah, that's all the same. Even though it doesn't say time channel 3 here. Time 1 channel 3 is not actually there, even though it says it's here. Huh. PE14. PE14 is somewhere else. E14 is on D31. That's why. Where the heck is D31? D31? IO shared between... Yeah, that's fine. D31. I think it's on the other side. I'm gonna follow that. If I'm gonna follow this, then D31 should be down here. One above ground. Nope. That wasn't it. Okay. How about PE14? I mean, that definitely has to be this one. PE14. Maybe I'm too low. There's a ground directly across, and then there's a ground here. Oh yeah, it's way lower. There we go. Okay, that should be it. There we go. So, this is supposed to be 250 milliseconds. This is 247.5. This is supposed to be 618. This is this is supposed to be... Don't tell me it's supposed to be what I think it is. Hold on. Hold on. I just had a realization. Back in the day, I ran my own code where I did math to calculate using the hardware timers what exactly my delay should be at. And I was noticing it was a little bit shy, you know, not hitting the exact value. Little did I know that I was trying to tune something that was inherently going to be wish-washy. The internal oscillator is not it. It's not it. The guy's comment about it being plus or minus 5 error, that's legit. So let's do some math here. Let's go back and do some math. STM HSI, don't use it. I think that is the key here. Just don't use that. You can do an external clock. I typed clock as I said clock roll. Calculator. Open up the calculator. Come over here to my dev scene. I want that. So, plus or minus. Let me make sure I can get his quote exactly. Plus or minus 5%. So if you want 200 millisecond, not 2000, 200 millisecond, and we did 5% of that. Ooh, that's a big range. That's a big range. Maybe I'm not reading that correctly, but maybe that's off of the clock signal. So if the clock signal is 100, it's, you know, this, and you took 5% of that, you could be off by 8 million counts. That seems wild. That seems really wild. So I was tuning something, not realizing that it all has to do with my timer, my clock. It makes me wonder if my millisecond library would have been slightly skewed if I used it on a different day. I would like to think the temperature, it would. So that's a little bit of a bummer. But at least that answers that question. I'm over here so eager to write off Embassy, when in fact it's my hardware this whole time. It's the hardware. And we learned something new. Your hardware can be off. Wait, looking back to this waveform, 250 is what I'm guessing this one's supposed to be. 350, I think, is this one. I'm gonna guess 600. I'm gonna guess 1 second. Those are so far off. That's really unfortunate. Can I look up for a high external clock? Does this thing have an external clock? I would really like to see that. Okay, 3 clock sources are described below. HSC is a 16 megahertz oscillator. This clock is available depending on the target 32 series microcontroller used. So let's go to the HSE. Onboard oscilloscope crystal. And it's saying the configuration depends on the series microcontroller. To help select the crystal and its associated capacitors, refer to this guide. We don't need to do that right now. The crystal might have the following characteristics, and they recommend this exact oscilloscope. I'm gonna assume that this is not on my board. Let's look. They're saying X3. Let's see if we can find something on the label X3. That didn't take long. I don't think it's going to show up on the camera that well, at least. But right around here, there's a spot to put X3. These 4 pads. They're like little gray dots or silver dots. But there should be a big square shiny dot here instead of 4 small ones. The 4 small ones are the solder pads, which means that I am constrained to just using my internal clock. Unfortunate. They're saying there's 4 ways to configure the pins. What do we got here? I might be able to use one from here. What is this? The MCO output of the ST-Link MCU is used as an input clock. This frequency cannot be changed. It's fixed to 8 megahertz and connected to the oscilloscope in. To use this clock source, you can do this configuration. Which is 1, but we don't want to do this. What about this one? Input clock from an external clock through PH0 on expansion connector this. We're not doing that. And then HSC not used. This is our case. If I were to go in and check these, that's what it's gonna be. Real bummer. Bummer, bummer, bummer. That's funny. So it advertises that you can clock up to 160 megahertz, but it doesn't actually perform well at that range. I wonder what this example defaults to. If we go into our clock configuration, oh yeah, we already saw it's 160 here. Well, oh wait, HSI. Okay, I misspoke. HSI is the internal one, and it looks like it's able to multiply it up to get 160 megahertz. So if we gave it an external clock of 16 megahertz, it could bump it up to be 160. Do they recommend a particular crystal size? They might have the following characteristics. Okay, let's go look up this one. Let's go look up this one. Since they probably did a bunch of testing with this exact module. Ooh, 0 in stock. Everybody, welcome. Wait, what the heck? Why does it think I'm in Bulgaria? Does it matter? If I go to US, is it going to change? Oscillator? Gosh, I can't forget dog, that's funny. I wonder if there's zeros in stock because of the exact one that I chose. What is NDK? NDK America? And then let's do... These are all grayed out, lol. Are you kidding me? Let's just do in stock. Let's see what they have. They have some really low frequency ones. About 80 cents. This one's $1. Dang. But yeah, it's kind of not easy to see on stream. This is the average engineering DigiKey experience. Nothing's in stock. Things become obsolete because you're using an old data sheet. Oh, this looks fine. I don't know what was going on the other page. So if I go to... Oh, they don't have an even number. Okay, well this one was saying that I could use up to 50. But it's not actually letting me configure anything. I wonder why I can't click HSE. HSE, yeah, like it's completely turned off. What if I go over here? Do I need to add something? No, we're not really seeing that. System core. Nada. Sys. Nada. Utilities. Nope. Link list utility. What the heck? Did you have some like hardware for that? Yeah, never mind. It's a little bit of a tangent, but I think it's gonna benefit deving. Surprised they don't have a more accurate one, I guess. 3,000 in stock, jeez. NX. So let's see if this is the similar part number. Not even close. Not even close. This says RN. Okay. What if I do this part number? Is this gonna be something? Oh, this is something. All right, because this is 0 in stock. This is that exact 16,000 megahertz. I'm gonna guess the reason you can't find it is because it's... Oh, hold on. I think it's because it's listed in the same data sheet. This one looks similar. Ships immediately. Okay. I wonder how easy it would be to solder this or not. 8PF SMD. 8PF SMD. Okay, so what's the difference here? This number's different. That's the difference. 200 arms. To me, they have the same detailed description, but there's clearly a difference, and my guess is it has to do with the statistical difference of accuracy. Let me see. Is there a data sheet for this? I'm not really seeing one. I feel like there's normally a button here. I guess I can look at these down here. All these appear to be the same. Yeah, I don't see anything different. The difference is one's in stock, one's not. Okay, I will probably... Oh, it's a dark mode. Sweet. I will probably add this to a bomb off stream. To get that for next time so we can get some more accurate deving on this board. I didn't realize this is what was going on. That actually makes things a lot easier to use my library though, or not my library, but the library that exists. Because I don't really need to do much now. So, all right, cool. I'm glad that we ran that example. I'm gonna go and close a bunch of stuff that we're not using anymore. And that's why having the ability to validate using a logic analyzer, that's why it's super valuable. If I didn't have this, I would have no idea to know that this is off and how off it is. So I think that was worth the investment. That already saved some troubleshooting down the road. Okay. So let's do a git fetch all. I want to reset this. So I think it's git. Let's see. How do I reset a branch? Reset branch. Yeah, git branch. Reset hard origin. Git reset hard origin main. All right, there we go. This was the original blinking example. If we wanted to do a different example, we could. But I'm not going to do that. I'm not going to do that. Okay. We're not going to do USB serial. We are going to probably do... What would be useful right now? What I really want to do is see how I can hook up my microcontroller to talk to this. To this guy right here. Because this is a very fun and bright thing. And I would use it a lot. So the cool part about Rust is that there exists crates that people have worked on already on crates.io. And you just might be lucky enough to find a example or a crate that somebody made to work with your chip. So lucky me, this chip right here may have a crate for it. Spoiler alert, it does. Go ahead and remove these wires since I'm not going to use them right now, except for the ground we can remove because that's easy to spot out. Okay. Tuck them away slightly. Okay. Fortunately, the name isn't going to show up on the camera, so I'm just going to go ahead and search for us. This is the Max 7219. And look at that. There exists multiple drivers that people have made, because multiple people wanted to try it. One of them has a little bit more documentation. One of them is downloaded significantly more than the others. This one was updated 15 days ago. So we can kind of pick which one we want to use. Well, this crate was built to support multiple displays. It's never been tested using multiple displays. Ooh, this one's built off Arduino. We're going to pass on that one. Don't want to be doing that. I think this is probably why people use this one. This one is using... I hope that's just an example. I see a RISC-V. We don't have a RISC-V. We have an STM. I don't think it matters, though. Okay. Powering on and off the Max chip. Basic commands for setting LEDs on or off. Chaining support, so I can support up to 8 devices. So here's their example. Also, is there a dark mode for this website? I guess there's not. Go to the repo, it'll be dark mode. Rust SCD components preconfigured crate for RISC-V target. This might be specific for RISC-V, which could be an issue, but that also means we could make a port for a different. Interesting. They have a dedicated repo just for the example. Kind of surprised by that. There's embedded hell for Rust. Huh. I'm not sure what's going on there. Docs. Here we go. Jar is built using embedded HAL, platform agnostic. Okay, so that means... Oh, still not big enough. Platform agnostic means that we should be able to use it for our project. And... it looks like it might be pretty simple to access. It's just that our example is written in RISC-V. So I just need to adapt it if we see something that we can't do. Okay. I have an idea where we add another file in here. We're going to call it Max17. Is it 2179? What the heck is this called? 7219. All right. 7219.rs. And to make things simple, we're going to copy our boot, which is our extremely basic example. Maybe maybe this one would be better. This would be your absolute basic example. Just make sure we can still build. We're gonna go ahead and do cargo clean. We're gonna do a git clone, not git clone, what am I saying? we're gonna do a cargo run dash dash release dash dash binary of max 27129. This should compile only this file, which is the same as the boot example. We just want to make sure there's no hidden dependencies that we don't know about. Oh, oh yeah. Wait, I actually got an error, which I think is because we reset the repo. Yeah, we did. We gotta go back in here and retype in this stuff because I mistakenly deleted it. So 7.5 CI, I think is what it is. But at the same time, we're gonna do dash dash probe and the 0483 colon 374E. This is more of an exercise just to see if we can import stuff just fine. Okay, that looks all right. Then we go to here and update this to be 75ZI. I'm pretty sure we're gonna have to update this tag, but it's all right because the compiler will tell us. It'll tell us, which is really nice. It needs to be TXQ. TXQ, which word for word isn't exactly what I see on my board. The T isn't really on that board, but it works. Okay, that compiled and it is spamming that. Holy moly. Is it resetting it every time too? Is that what's going on? No, it's just looping indefinitely. All right, cool. So we got this. This is a program that doesn't even use anything besides just the memory X file, which I like. You know, you can really keep it to the bare minimum. Hold on, let me go to the repo for Embassy to get this .vs code settings.json, because this is a little bit annoying. Okay, we're gonna make a new folder. .vs code. This is just going to get rid of the squiggle here so that way our compiler can work. VS code, and it's going to be new file settings.json. And in here, we're going to uncomment our chip. We're going to change this to be our chip as well. So it'll be U575 CI. Is that what I had on this page? Not that page, but this page. CI, yeah. Okay. We're gonna uncomment this target to be our target, and then we're gonna keep everything else. Okay, we'll restart the server so that way it's able to parse. I think we're gonna close that too. Blinky. So restart server. Okay, didn't like that. We should. Your tool chain set up correctly. Oh. What if we did this? Would that change anything? Okay, what if we did this? That change anything? None of the selected packages contain these features. Rust Analyzer cargo features. None of the packages contain these features. Well, that's not true. What if I just commented that out? Okay, that looks like that worked. Cool. So now if I come into here, yeah, sweet. All right. Hopefully we don't have to change that ever again. So we want to figure out how to integrate our first crate that is not Embassy. So I think I can start by at least coming into our cargo. No, not cargo, sorry. Our crate.toml and adding it on this page. So we have a lot of extra junk that is getting added, which is fine. But if you really wanted to make this image size much smaller, you probably would want to remove a lot of this. We're going to add our library down here. Hey Gary. So the tutorial videos you sent, they probably weren't the most helpful. They're helpful in the sense of I saw what exists on YouTube currently. The issue with the ones you sent me are they're written for Arduino, which we don't use. I don't like Arduino. Arduino's fine for starting out, but yeah, that's okay. That's okay. Lay him off. Lay off him? I'm gonna lay him off. You should have got me a better video. No, I'm just joking. Okay. I'm gonna make my own path by creating something brand new. We're finally into new content. Content that's not dependent on tutorials, hopefully. Especially Arduino tutorials. So theoretically speaking, if I were to incorporate this crate by calling this function, what would happen? All right. I wonder. So this is no, this tutorial. There's no tutorial here. This is the tutorial. No video. The VOD is the tutorial. Just this raw, live, debugging full session. Interesting. This is the first time I've actually seen a file with good comments. This is the first time seeing this. First time hearing of this. This is great. I don't know why Embassy couldn't do this. This is the like Doxygen style. A study guide? Yeah, there'll be a study guide. It's because of how glorious Rust is, the study guide will be the auto-generated documentation. That is the study guide and this video. Those are the study guides. Okay. I'm gonna look at I'm gonna look at this to figure out what I need to do. I think I need to get this struct and base everything around this. Handles communication with the MAX 7219 chip. Each display can be connected in a series with each other. Okay. I don't know. I'm guessing you put these chips in series. If it's not that, it's the these segment displays here, you put these in series because this is technically two separate segments, or sorry, modules that I just put in the breadboard to look all as one. How about we do this? I'm gonna look up the data sheet for the segment display, so that way I can find exactly what we need. Is there a date on this? Oh, I didn't mean to open that. I gotta look at my old search history. Jeez. January has a lot of WoW. That was Big Bear stuff. A lot of YouTube too. These are registers. These are ISRs, NeoVim. I remember that era. Clang. NeoVim Chad. Lots and lots of YouTube. YouTube Shorts even. I search segment or display. Okay. Okay, I'm definitely in the right region here. MK Ultra? Oh, I think it's this one. Okay, it could be this one. I don't know if it's exactly this one. I think it's this one. No, that's okay, I'm in the right realm. But this looks silly. This one? Segment display LED guide. It could be this. This on the main screen. Theoretically, we could have a pinout that looks like this. I wouldn't count against it. I could totally see this. I could then see this being combined with that. So we have the 7219. Oop. Got to zoom it in. 7219. Oh, it closed out of it. What the heck? Oh, closes out each time. Okay, let's go new tab. There we go. So I need to use this chip, which I've already connected on the circuit in this bottom area. Okay. This circuit on the right here. Connected the resistor and... Oh, interesting. There was a different circuit graph I had that showed to use a capacitor with ground. Wonder if I read that somewhere else in this data sheet. Because that's always possible. Like an example circuit that's a little bit more detailed than that one. Oh yeah, maybe it's here. I think it must have been. Oh no, this is... Hold on. Oh yeah, it was right here. This is for a serial interface. We don't need to actually connect to that, but the 1 microfarad capacitor helps with the noise on our supply. It's just a nice little filtering. It doesn't hurt. we need to connect. We need to connect these wires up though. Currently, don't have them wired up. So I am going to put on the circuit cam because we need to connect a bunch of these. And it's not going to be fun. I have these yellow wires coming out of all the bottom slots and these greens going out of all the top. Actually, I think our green ones correspond to all of our digit spots, right? 1 digit, 2 0 1 2 3 4 5 6 7 digit positions, and then our yellows are the actual segments, being the top of the 7 segment, the right of the 7 segment, the bottom right of the 7 segment, the middle of the 7 segment, each of these segments. So if you wanted to turn on this digit position and turn on some portions of it, you can wire it up using this, and then it just goes across the whole wave. So this thing turns, it runs. It's on a clock signal, so every so often it'll turn this on, then I'll turn it off, then I'll turn this one on, then turn it off, turn this one on, off, on, off, on, off, on, off, on, off, on, off, but really, really fast, so it looks like it's on consistently forever, like frame rate in a video game or hertz on your monitor. It's the same principle. Instead of having a bunch of wires going everywhere, you just cycle through it really fast so your eye can't detect it. But yeah, this part, well, maybe it's better if I do the dev, because at least you can see what I'm wiring up. I think this might be better, because it's gonna be too small to even see the wires. Okay, I'm copying this left diagram. So what I need to do is figure out where pin 1 is, which you can check by looking at the dot. And then looking at the dot, and then seeing how it matches up with the diagram. So pin 1 is going to be our top left, which we have data in. So this most likely is going from our microcontroller, where we have chip select. Unless this is only on the max 221. Hold on, let's go ahead and check the pin out up here. Okay. Pin 1, D1. Pin 1 is always the top left once you find the dot. So this is our serial data. This is going to talk to our microcontroller. 2, 3, and all these other digits is our digits. So that's going to be all this side, which are yellow. Our yellow are our digits. And we have some grounds, which I've already hooked up. And we have a clock, serial clock input with a 10 megahertz max rate. Okay. 10 megahertz is, let's see how many seconds that is. 10 megahertz is 1 nanosecond. Is that what I'm saying here? Yeah, 100 nanoseconds. My bad. 100 nanoseconds. I fear that our embassy framework will not be fast enough. That's right. I am a little bit afraid. I worry that it won't be fast enough. So I'm going to quickly come into here and see if they mention anything about clock. I'm gonna search clock. The clock pin. The clock pin. And we have, that's it, just this clock pin. So we have to implement this here. I think we just choose our pin maybe. And maybe use Embassy's SPI framework. From SPI. Construct a new driver instance from a pre-existing SPI in full hardware mode. That could make sense. Because it would make it a lot more simple. Oh, wait, hold on. Test? Set test mode on/off. If you set it on, display to an address as connected in series is on. Turn test mode on or off. Is there test mode just built into this chip? Test. Oh yeah, there is. Oh, that makes it so much faster. You don't even have to implement anything. You can just run this test. Test mode. Display test. The display test register operates in two modes, normal and display test. Display test mode turns all LEDs on by overriding but not altering all controls and digital registers. In display test mode, 8 digits are scanned and the duty cycle is 31/32. Oh, 31 out of 32? Is that what it's trying to say? Table 10 lists the display test register format. Number of digits displayed, 1. Oh wait, no, table 10. Is a 1 and 0? So, oh, okay. This is gonna be set to 1 if it's in register, or if it's in test mode. That makes sense. All right, no biggie. That is cool. We can actually accelerate and ensure that we connected everything in place before we start writing code. This is such a quality of life to our situation because we're wiring it up by hand. Sometimes you can't guarantee that you wired it correctly, and you don't know if you have a hardware bug or a software bug, and you have to weigh both possibilities. But if you can use just a quick hardware-based test like they made on this chip, then you don't really need to do a lot of code. You just need less code and you can focus on the wiring. That's awesome. I really appreciate that. All right, so if we have test here, I'm gonna search for the word in test in here. That turns test mode off, which we don't want just quite. Set test mode on off arguments. So you call this function test, which takes the arguments address and on. On is bool, so we want it on, so we'd say yes for that. You're going to pass in a max7219 struct here because it's asking for self, so your instance of yourself, and it's going to return the result, which result returns two different values. I'm not sure. Result passes either a true or an error. I'm going to guess if it's an okay true, then it just returns whatever it wants, but if it returns as an error, you pass data error, which data error corresponds to something. Yeah. Okay, cool. So is it just new? I think it's just new. I think all I need is to call new. And if we want, we can also just look at his example here. They configured clocks. We'll worry about that in a little bit, but to get started, he calls this function. Oh, he doesn't even create an object. He's just saying, hey, create. No, wait, this is an object. What am I saying? He creates an object, calls it display. And then display has some of these functions. And in their case, they power on the display. They write a string. Interesting that there's a function to help you write a string. That's pretty nice. Please help. Write given octet of ASCII characters with dots specified by third param bits. Okay, so there's a dot here. Not sure what 0 is. Set display intensity lower, so the brightness of it, aka how long it turns on for. If it's on for longer, it's gonna appear brighter. Actually, if there's more space in between, if you have a slower frequency, it's gonna be turned. Oh, let me think about this. If you're running through it really fast, you get the illusion that they're all on at a brighter rate. But if you have a slower frequency, one of them will be on slightly brighter, but in the general average, it's going to be dimmer because the time it takes to get a full cycle around is going to be longer. So this is basically increasing the frequency. If you're going to increase the intensity. In your case, they set it lower, so it would decrease the intensity, or decrease the frequency. I wonder if I can just use these pin macros. If I were to remove hello world and our loop, and we just leave loop empty, we go max here, right? And we want to call from SPI, I want to say. We'll do test when we want to do writing, but for now, well, maybe we do pins just to keep it simple. Function from pins displays use size. In their case, the number of displays, we have two displays. We have two displays, data, CS and SCK, unwrap. You can call that, but data, SCK, and CS we have to define. So just like they have here, let data, you're going to be equaling this to some kind of pin, but we want it to be SPI. Now this is where we need to see how Embassy uses SPI. Because I might be able to just bypass the Embassy completely, but I need to make sure. Why is it talking about time? We want SPI, right? SPI. And we want Rux SPI driver. When we go to Blinky, we import we're gonna go ahead and that how that is and import it this way. Embassy STM SPI and we're going to want. Well, how did they do Blinky? For Blinky, they passed in some enums. So let's get some enums in here. The symbol for enums, I believe, is... What is enums on here? I actually don't know. Is it the phase and polarity? I think that's it. In this case, they say enums is phase and polarity in the bit order, yeah. For you to make a new SPI instance, you have to pass in these. Whereas in here, try to make a new tab. Instead of SPI, we look at GPIO. Where's GPIO? Modules, GPIO. GPIO had us taking in these enums. So that way we could handle a struct for output. Output new. Pin, output speed. So we need to populate all of these. Actually, we can just do TX only. So we need to import all of these. Peripheral. That's slightly new. Oh no, it's the same. Thank goodness we had this Blinky guide. It's Blinky example. Because it gives us a better look at how a working example is structured. Here's our pin that they chose. Here's it being low. Just gonna replace this with PC7. So let's do it like this. Instead of from pins, we'll do it from SPI. Because we're gonna incorporate, we're just gonna import SPI. Which I think I can do it like that. And for putting them side by side, we need to set a P to make it so we have a simpler looking variable to access our peripherals. Initialize our peripherals and call the default config. I don't know if you really need to change that much. I haven't really looked into that much, but that's okay. Open ChatGPT to solve. Unfortunately, ChatGPT is a little bit behind on Rust. Normally I do use ChatGPT to solve a lot of times, but recently ChatGPT can only do up to 2022 code, and this is more recent than that for Rust. But in the future, I'm sure it would have an example. All right. Snapchat chat. That's a good point. That's a good point. Snapchat's bot could help me out quite a bit. So we're going to call this my SPI. That's, I think it doesn't like camel case, so I'm going to do my SPI. I think it gives you a legit error about that. And instead of output, we're going to do this new TX only, which is a call of itself. New? Is that right? New? Nope. Okay, that doesn't work. How can we do this? New? Can I import it here? New? Interesting. I guess I need to import something else. Somehow to get this, we need to... Oh, well, first we don't want that one. We want the TX only, not the one without the clock. We do want clock. We want clock very much. Okay. It'll be config. I would imagine it would just be SPI. How about we do this? Just import everything. Oops, SPI colon. Data type will be SPI. Will this work? SPI. New? Okay, yeah, this is right. All right. This is where we need to pass in stuff. So, okay. We want to pass in P dot, and then we need a name, the exact pin. Now, to save some time, I think I'm going to open up their example if they have an SPI one, just to see how they may be calling that in. We want since SPI. There's any special way. So they just say the exact pins. They looked up which pins SPI can connect to. Okay. Even have a frequency configured here. That's interesting. Is it SPI config? Huh. I guess this would be helpful to max it at 10 megahertz. I might do that. Yeah. Okay, so we now need to open up the data sheet, unfortunately. And in our case, since we are slightly limited on our pin IO, we're going to look up which pins SPI can go to. These will do. We'll do SPI-A, which all look to be part of SPI-1. Just to make sure, we're going to search for SPI-1 specifically, which are all here. Okay. So we're going to do PA5, PA5. Let's see. What is this fine? I don't know if it's liking that very much. We'll just continue on. Oh, hold on. This should be peripheral. The peripheral itself will be the data out. If I'm not mistaken, right? Data out. So, hold on. This is the clock. Clock is PA5. P.PA5. 5. Actually, let's call it PAC, so that way we at least have an idea that this is the peripheral access crate. MOSI is PA7. PAC.PA7. Our CS is... Oh, maybe that's what this one... Peripheral... This is the clock. MOSI, MISO. It's not chip select. Maybe this is one that doesn't use chip select. TX only. We go to the data sheet, or not the data sheet, but well, let's just say new here. If we go to, is this GPIOs? Yeah. There is no chip select here. There's no chip select here either. Oh, it's RX only. Chip select is also not here. Maybe the peripheral is the chip select. I'm kind of thinking it might be. So, huh? Is there any kind of CS pin? There's CS pin. So this it is brought up. Wow, it actually tells you the exact pins that it can even be. That is a huge W for Rust, or at least this framework. I don't even need to look at my data sheet. I literally just look at this. We go to config. What does it look like? Mode, bit order, frequency. What kind of modes do we have for SPI mode? Probably just gonna keep that the default frequency. We'll probably put it at 10 megahertz, like it said it could max out at. So wait, if I don't need, if I go to SCK pin here, I could just look this up. Wow. So let's compare. So I think a clock pin could be PA5, which there it is. Wow. Cool stuff. Let's see. This needs to be peripheral. I wonder if for the example they have, if I can match it up. SPI3. So you're choosing which SPI peripheral. Okay. Okay. That makes a lot more sense. So this would be pack.spi1, I think. SPI1. And then this, we're going to do no DMA. Right? No DMA. We're not using direct memory access for this basic example. And then config, we're just going to do, we're gonna do what they do here. Configure it. SPI. So you can do it like this. Interesting. Is this mutable? It is mutable. They put it as mutable. SPI.config. No, config default. Default. And then we do SPI config dot frequency. And we set it equal to hertz. We're gonna do 10 megahertz. Cool. What else are we missing? Oh, the config. Yeah, we gotta pass in the config. Pack dot. Oh wait, not dot pack. We do SPI underscore config. Passed it in. Okay. My SPI. Let's do my underscore SPI. And oh. What's going on here? Variable does not need to be mutable. Okay, fine. What if we don't make it mutable? We're getting yelled at still. This is intentional. Prefix it with underscores. It doesn't like how to name it. So we'll go ahead and do max 7219. It's just because you're not using it. You think so? It is streaming time, Jacob. It is. Yeah, you're probably right. Residential prefix it with underscore. Yeah, these are all just things. Okay. My SPI, then we'll keep it like that. Project's going all right. We're trying to write our driver to turn on the 7 segment displays using an external library. Okay. Oh, this is where they do chip select. They do it in a separate line. I should have just looked at this example. Yeah, I know, it's pretty exciting. All right, we're gonna do that. Let CS equal to, I guess we can, apparently we can just do this. Maybe that's what we'll do. I was thinking that's going to be a keyword used by other stuff. Output is just like you're defining it to be a GPIO, which makes sense. Then we can do new, and then we need to figure out what this allows us to do. Chip select is here, D10, which is PD14, PD14. And then if we were to go to the data sheet of, not the data sheet, the documentation, and we went to, if we went to the CS pin, these are the valid CS pins. PD14, I'm not really seeing here. Maybe I'm looking at documentation wrong. This is our chip. Where were we? You want to look at the Adobe. Where's Adobe? There it is. SPIA, PD13. Yeah, it's right here. You feel like you're surfing in CSGO. That's true, yeah. I decided to choose a different playlist today that just sorts by popular, so ideally there's less obnoxious music. That's funny though. That reminds you of surfing. I could totally see it. Too bad I don't gotta cram it. My knife dream been ended short. PA15. Yeah, I'm not sure. I think I should just try this because this is how it says to wire up. I wonder if it's going to yell at me. It's not object safe. I think that means that I can use it still. And it's not going to yell. Alright, whatever. Anyways, we declared our pin. Level is going to be high. Because I believe it's... I actually don't know. Speed, we do need it to be very high. We need this to be very high. All right, we're getting yelled at. What are we getting yelled at about? Use. Oh, maybe it needs to be all caps. Nope. It's because I'm not importing it probably. Yep. We do it like this. We import output, we import level, we import speed. Okay. This should be pack. Just realized. And these are just not being used right now, so it's fine. Okay, I think we're good. If we go back to mode. No, not mode. What are we going to? We need modules, SPI, and maybe just SPI driver. Yeah, I think it's this. Yeah, we created TX only. Okay, I think that's fine. So now, this is where they begin to do their CS or their SPI example. So this is where we pivot and look at this driver now. They created this display, which we're going to do from SPI instead of from pins like they did. Hopefully this works out fine. So we're going to do let display equal to max 20p. Oh wait, we want the full thing. 7219. I don't know why I'm saying P. There's no P even near this thing. from SPI. Okay. So it's saying we need to pass in the number of displays and the SPI thing. So we have 2 displays and SPI is literally SPI. All right, we're not getting yelled at. Pretty good. So then if we go to display dot test, no, colon test, nope, doesn't like that either. They have display, make sure to power up display. Well, okay, display dot, and we should be able to run it. Maybe not any of these. I think this is just pulling from Rust in general. I think we need very specific ones. I'm surprised there's a power on. So if I did display power on, there is no power on. No method power on from the enum result. If I did make this a mutator. I think that's why. Nope. Nope, still doesn't like it. Okay. Let's look at the documentation. How is the support for Rust with stuff like this, at least compared to C? Okay, wait, hold on. Moroider from SPI is fallable. You need to extract the value from the results. Extracts the value from the result. I see a result here. So the result either passes. Does it show it here? Oh, here we go. I see. This returns a result itself or an error. Well, quickly to answer Heathcliff's question, support for this, it can be limited. This particular thing, Apple, fallable. Fallible. I see your point. Yeah. Support for this is pretty minimal. You have to be lucky, kind of, because this particular library only has about, this particular crate only has about 4,000 users. At least has been downloaded 4,000 times, or maybe it was 8,000 times. And I don't really see a whole lot talking about this particular crate. Granted, I haven't really looked into it. I'm just making an assumption, because when I looked into the embassy crate, that did not have many users posting about it. Most of it was just the repo itself. I had to instead go on Discord and talk to the creator of the crate and ask questions to them directly, which I got very lucky that I was able to find them on Discord. But regardless, yeah, the support is a little bit tough. In C, you just use ChatGPT. That's your support. It's just 9-day difference. Oh, really? Few crate downloads are from CI as in crates.io. Okay, dang. Are from CI. Wait, could you elaborate what you mean CI? All right. Thank you. Thanks for stopping by. Thank you, Heath. Appreciate it. Continuous integration. Oh, okay. Okay, I see your point. Every single time somebody is polling the crate for their pipeline or for their workflow on GitHub, it's counting that. Okay, then even less so. Support. I didn't know that. That's some important feedback. So yeah, it just furthers the point. All right. So we're trying to figure out the result of this. So you're saying the result of this fallible. What does that mean? Oh, it's... Oh, so you need to make sure that it passes. It won't just let you automatically send it into the display. You need to run the code that checks if it's okay. If it's okay, then set it to display. Otherwise, do something else. Oh, that's right. I remember reading this a little bit in the Rust book. I'm going to pull that up right now. We don't need this anymore. Although this one actually has the same kind of thing. Surprisingly enough, this has the same similar kind of thing. I was able to... Maybe it's because of what data type I sent it to. It's something to keep in mind. Yeah, I mean, that's a good point. I'm not sure how many it would be from CI. But that definitely could spike the numbers. Better result. Alright, so this enum result need it to be okay. Here's an example. Let X result is this. Well, that's assigning it a result. Was returns true if result is okay. Assert equal. Oh, this is like a testing thing. Hold on. Yeah, I'm still pretty new to Rust, so if you have any tips about... Is that what I needed? If you have any tips about setting up this stuff, definitely feel free to comment it. So this is the self. I recall now. This from SPI returns, where'd it go? Self if it passes, data error if it doesn't pass. So we needed to have display be a data type of max, which then just redid everything. So then if I... Oh, but it still doesn't have the power on. You can try to... Okay, wait. You can try if let OK display equals from SPI, yada, yada, yada. Let's try that. We want if let if okay display equals this. Expects a block here. Is this where I would then use display? It has to be if let okay. And then inside of here, we run our code. So then I could use display probably. Display dot test. Maybe that example they have is just a little bit. Oh wait, power on. Yeah, okay, wow. Cannot borrow, display is mutable. Okay, do I have to do if let mute? Am I allowed to do that? Ooh, you can't do that. Mute must be attached. Add mute to each binding. Do mute before display. If let okay mute display. All right, what we got here? Okay, I think that's fine. So let me break down and see how this makes sense. So we know that this function returns a result, which can be an okay, or it could be a fail. We just are writing code for the okay situation, so we're testing a condition where you're saying if it's okay, then we enter into here and utilize this data. If it doesn't return okay, then we don't even do anything with it and we're just fine. Okay, that's pretty neat. But what if I wanted to, like, do I need to do if okay always? You're gonna want to figure out what to do about errors though. Okay. I guess if we have an error, just for now, like if I do else, right? Am I able to just do info display error? Display init fail. Would that handle our error case? I mean, data error, I would like to see what that is. Data error is just part of the, oh no, it's a part of our repo. An error occurred when working with SPI. So it looks like I would probably want to print out error occurred, data error for SPI. Oops. Max. That'll run the error case. Sweet. Max error. And then we want to print out these variables. I've never actually seen if I can use the macro to pass in something. Ooh, it would be self. Actually, I'm curious. How could I tap in to the results that this passes back? This data error. Data error is a value. I need to put it into the else situation. This is probably where it would be good to bring up the Rust book. If you want to actually print the error, you may want a match statement instead. That's some match. I remember it's like a switch case situation. And it's actually, maybe we just want the regular Rust book, not embedded Rust. Let's do Rust lang. This one? Oh, well, I can get there from here. This isn't quite what I was looking for. Read the book. Read the book. And then we search for... Okay. Result inspect. I could do result. Let's see if they quickly have an example. The search is not that great. Error handling. Thinking about it, I think I skipped this chapter, so that's probably why I was a little bit lost. Here they have a match. Okay, I think you're right. So instead, if I do if I do this, I'm just gonna go back. Let display. We're probably gonna need to make this mutable. Let mute display. Why are my tabs? Tab size should be 2. Why was it all jacked up? Why is it jumping to 4? I'm not sure what's going on there. That's weird. Okay, if it's okay. If it's okay. Interesting. They have this file here. Oh, we've got the match keyword. Let is equal to match. Kind of want to pass. I'm gonna pass in display. Well, if I do this, okay does nothing. But if it's an error, SPI error. How that works, you pass it in over here, and then I can do this info where it's data or the CSP, SPI. Oh, I can't do that. Can I pass in a value to arrow? Or sorry, info? Yeah, I can apparently. Args. Interestingly enough, this isn't quite how you do this. Can't I do something where it doesn't do anything when it's... What's that enum? It says OK file. OK file. And then it sends over file. Like the option enum, result enum and its variants have been brought into the scope. The result is okay. The code will return the inner file. The code will return the inner file value out of the OK variant. We then assign the file handle to the value. Sorry, the file handle value to the variable greetings file. Oh, okay, so you choose one or the other. Doesn't it already do this? Isn't this already happening when you call the function? Oh, wait, hold on. So this file here. Okay, hold on. If we do display results, display result, we then can say in the OK case, we want to create a new variable where we say display is passed over. Okay, hold on. Let mute display equal match of display results. And then that display result, is that right? Match display result, yep. And then if this is display result, you do OK. And you're gonna pass in D, let's just call it D. D gets pushed out. Otherwise, error. Is it like this? Error? Yeah, error. Oh, yeah, error. We pass in this error, let's call it. Error comes in through here. And we do info. Let's just start off with saying info display error. Let's start with that. Just to make sure we have this interpreted correctly. I misspelled display. That is a display. Okay. If I do display now, display power, no, hold on. It's not quite. Oh, because this is still matched. That's why. Oh, shoot. That added a lot. Okay, display dot power on. There we go. Display power on. It doesn't like this. It thinks we should do something else. It thinks that maybe we should print out error, perhaps. Oh, wait. DFTRT. Ah, okay. We need, oh, it's right here. We need DF. I should be bringing it in. Yeah, it's should bringing it in. There's a chance that I'm not using that right. Display error. What did I not like about this? Match arms have incompatible types. Expected struct. Both match arms need to return the same type. So this needs to return data error. Okay. So I need it to return. You get around this, you can panic on the error case as the example shows. Okay, yeah, let's just do that. There's definitely some Rust misunderstanding that I have. Oh, I can look into that later. It says panic. As the panic unwinds the stack or boards, as likely the case for you as you're doing embedded. So panic would leave out of this whatchamacallit. Oh yeah, I would leave the stack. Yeah, that's right, because you entered this the panic handler. Okay, I guess that'll work. Abort. See, panic. If I did this, would it yell at me? DFMT macro. Okay. Use this. Display error. I could do. Actually, we'll just make it like that. Doesn't like that. Panic is ambiguous. Could be referred to a macro from prelude. Panic could be referred to the macro imported here. DFMT panic. Cool. This result may be an error variant. That is true. Although we would actually hit this case, so I don't think that's actually true. All right, cool. We progress on. So since we do this power on, I actually don't know what this unwrap does. Unwrap returns a contained okay value. Unwrap panics on error. Oh, okay. Thanks. So theoretically, could it have done unwrap over here? Wouldn't that have worked? I feel like you said something. Oh, you said result inspect, but would I be able to unwrap on this from SPI? Oh, that's exactly what they did. Yes, but unwrap isn't the greatest. Greatest because you're not actually doing any error handling, or because there's some other stuff behind the scenes that is not clean. Address display to turn on. We'll do 0 and we'll turn is on. You're just blowing up the entire program. Oh. Yeah, that is true. I mean, and that's also what I'm doing here. So I guess I'm not really doing anything different except for putting a message and saying, hey, this is exactly what I want. Cannot find is on in the scope. It works though, which is good enough while you figure stuff out. Yeah, that's true. I definitely like the toolset that exists. I want to understand how I can utilize it a little bit better. Once I get this started, refactoring might be a nice help. Okay. But what are they looking for here? Oh, okay. Test is on. Whether to turn test. I think I just need to import is on. which would be, oh, hold on, I think I set it up here. Is on as a bool. Oh, okay. True. We can do this. And then we do unwrap here too. Because everything returns some kind of error. Dang. I can quickly see where this gets not out of hand, but I quickly can see where this like just grows and grows and grows. But because you know exactly all the possible pathways, you can really define the entirety of your program and see you could get away without doing any of that, but you would just lose that information. Like you wouldn't know that it's bugging there until you hard code that in. I can really appreciate that. That's kind of one of the main reasons I'm exploring this as a legit language to be coding embedded in. Intensity. Let's just keep the intensity how it is. Okay, I think this, let's just try to compile. I'm not gonna run anything because I don't actually have anything wired up just quite yet on the breadboard. Let me just go ahead and we're gonna do a cargo build of the binary. We won't do release. We're gonna do a binary called ours. Oh, I don't have my num lock on, and I just made my command go away. Okay, bin max 7219. Okay. As long as this compiles, should be good. What do we got here? Just an unused warning. This is fine. Unused import. Where did I import? Get rid of that. I don't know what, maybe that was from earlier. CS wasn't used. That doesn't seem intentional. Maybe it's because their example uses CS. I feel like I needed CS for something. Could have been that it's because their example here. Where's that SPI? Their example had us doing set low and stuff. I think I can just do it as this, where I'm just setting this pin to high. What I do want to find out is if our chipset needs it to be set chip low. Yeah, it looks like it's active on chip low. So we do want it to be low when we are writing to it. I wonder if this test does anything with that. It's writing data. Okay, I think we need to do chip select slow then. Where is that at? Here we go. We're gonna set this to low. And then was there any other warnings? Error. Oh, if this is intentional, prefix it with the underscore. Oh, because we're not actually using it. This should just be this perchance? Or maybe it's the naming. So we're going to build this again. Okay. Cool. Cool. That's what I like to see. Yeah, let's just do wiring. Let's see what happens. We're gonna go all the way to, no, we're gonna go here and see how it's wired up. So digit 0, we need it to match our actual digit 0, which seems to be the pin. They, for some reason, indexed by 1, 2, 3, 4, but it should be this topmost. So we need to start doing this. Would you prefer to look at the data sheet on the stream or the circuit cam? What do you think is more intriguing? In fact, let me move this chat down a little bit. Dev scene, circuit cam, alert box, chat. We'll do this one. Of course, I gotta see where the pins are actually lined up. Okay, it looks like they're at column 10. So I need to match up starting from this column. Go from there. I could have used smaller wires, but I wanted to color code so that I could at least figure out the functions of what the wires were doing. Okay, first wires in. Digit 4. If we're starting from 0, that'd be 0, 1, 2, 3, 4. This one starts at 30, row 30, the breadboard. It's really handy that they got these numbers on it, because otherwise I really would just be guessing. Get to see how bad I am at using these wires on the big screen. It's really hard to make it fit. The white doesn't even come up that well on the camera roll. Okay. Row 5 is digit 6. 0, 1, 2, 3. That would be 5, 6. No, 5, 6 would be this one. Now we need to see where that matches up on here. 6, or the second digit position, is 3 pins lower than the first one. Okay. We then need to get pin 2, which would be the third one in this row. And we gotta see what the third position is. Okay, it's the 5th one. For context, I am jumping back and forth between these two sheets. I'm seeing the pin here, seeing the pins on this side, and then connecting the wires to see where it lines up on this pin out. Digit 3. It's the very bottommost. Dang, this is annoying. Gotta wrap it all the way around now. Onto this side. Okay. Digit 7. Digit 7 will be the last one on this one. Ooh, we run into a situation where we might not be able to hit a nice in out. Which means I might route this underneath. Won't be the perfect connection into the breadboard, but we can sacrifice that. Gonna be floating and sitting on top of the wires, but the actual connectors that the sensor has or the display has, they're long enough. The leads are long enough. Okay. Wires are definitely not the best. Okay, digit 5. This would be here. Digit 5, I need to double check. It's 3 wires down from the first position. Had our first mess up where I plugged it in 1 row too short. Okay. And last but not least, need digit position 1, which is here. Okay. So theoretically, we should have all of the segment positions, or sorry, just digit positions wired up. So now what we need to do is wire up the individual corners. Let me change the screen actually. The individual corners, the segments. There'll be a wire for each, as you see here with the drawn on letters. So we'll be doing basically the green side, which is in my circuit, the top side, all these green wires. So starting in the top, segment D would be the bottom segment of the symbol. Oh, wrong one. Okay. Segment D. Connected to the second pin on the bottom side. It might be a little tough because I wired this to go underneath this random capacitor. Try not to short the leads. If I can. Okay. Now we got it coming out. This is where a PCB would be very nice, or a proto board or something to make the wiring cleaner. Breadboards can only be so nice. Okay, next is the decimal point. All these decimal points, which I now realize I'm gonna need to wire another wire from here to this chip too if I want to get this to work, because there's 7 segments plus the decimal point. That's 8. This is 8 wires coming out of my IC right now, and I'm not the same 8 wires that control this need to control this one too. I may just start with only controlling this to see if I got it right. But in order for the finale, I would need both. Decimal point comes over to working to the 3rd pin. Of course, all these pins are bent. Okay. Next one. E, segment E. So this bottom left corner, segment E is the 1st pin. I'm learning that wiring things, it's not as exciting. Not much to talk about other than my failure of dexterity. Segment C. Maybe if my mic was actually on my mouth, because I have to like move away to actually get in here. It's too far from my mic. I guess I would need to place where I'm clamping my microphone. I could probably figure that out off stream. Yeah, I'll figure that out, but yeah. Okay, what was I doing again? Let's see. Your mic is fine. Oh, it's more the not being able to talk, because I start to go over here and then it gets farther and farther away. That's what I'm referring to. It's just the physical placement. It's far away from my breadboard. Unless you enjoy the quietness, then that's fine too. Just enjoy the music. Okay, pin 4. Pin 4. Now we're on to segment G. Yeah, which one? The one that's going underneath? It is scuffed. It's really just forced underneath there. It's floating. Okay. Segment G. In fact, I should probably just pull this up more. Well, actually, I might have topside pins now. So this is segment G, which is the very middle digit or segment. Oh, that's on the bottom. This is what the glory of prototyping is all about. Just not focusing on beauty, functionality, and you beautify it afterwards. I have to be okay with that. Being a perfectionist, it hurts sometimes. Seg B, it's the top right one. Gosh, it's so packed right here. There's so many wires I need to get in here with my wire. I got lucky that there's just an open channel at the top though. We're actually fine. Extra column. In fact, ideally I should be going underneath these two wires. Right now this is above it. Wish I could go under, but we'll worry about that later. This one's gonna be segment F, which is the top left segment, which goes into pin 3. Okay, pin 3, last but not least, will be segment A, which is the very top segment, and pin. Okay. 4. 4 is ground. I'm gonna guess. Okay, I have wired it all up. I do need to see. I took out a capacitor, so I need to see where that capacitor could go. I'm gonna guess it's gonna go onto this circuit right here. I think it's gonna tie I set to ground. But let me go to a different section where they talk about that a bit. I think it has the ability to help us. Okay, that's with some actual transistors, or those buttons. Those look like transistors. I think this is what I was looking at. If not, I'm not really sure I got this extra capacitor from. Probably. Hold on. This is a 10 micro farad capacitor they have from ground. The thing is, I don't see where I actually got this from in terms of wiring it up. Oh. Okay, I guess an ad's running. That's a little bit shrimpy. I'll try not to do anything too important. Max 7219 data sheet. Data sheet. Is it this one? Oh, okay, here we go. Maybe this is where I got it? Or is this the same exact, like the same data sheet? It can't have been this. Couldn't have been this. Yeah, I really don't know what the heck. Okay, well, we can leave it out for now, I suppose. I'm just trying to think what... I would have only looked for a data sheet. I don't think there could have been any other documents that I went through. That's fine. All right. So I think I can just upload the code. Oh, no. I need to wire in my microcontroller. That's right. So this is where we go into the code here and look up these pins and how those wire in. So the first pin is our SPI. Oh, that's not a pin. Our first pin is PA5, which is our... this preview is kind of hard to read. It's our clock. PA5 is our clock, which then we go over here to see what PA5 is. PA5 is D13. I need more wires. I need wires from my microcontroller now. My microcontroller into the actual board. And this is where the magic smoke comes out when things go wrong. We're gonna do orange. Will that reach? That definitely will not reach. What if I bring it here? Might work. Although D is on this side, so we'll do it this way. Jumpers came off. Hold on. I got the feet on this thing. This thing uses jumpers to have a standoff, so that way you don't short all these pins on the bottom. I should probably 3D print a case or something for this. Okay, we got bad news. This wire does not reach. It is too short. We did something like this. I still can't reach. Like this. Off to the side there, I just shorted this capacitor so that way I don't short it on my own hands. I don't think it would hurt me, but I'm using the resistor to short it across itself. Okay. Yeah, I think I'm gonna need different wires. Isn't really looking like this is gonna fit. Oh, or I have more. These ones are even less, even more messy. Look at this. This bundle of wires in a plastic Ziploc. Okay, we're gonna use this blue one.
I'm not sorry 'cause that was intentional.
13 going in.
I meant every word
We need to
that I
connect
said.
it to
You get angry with me 'cause I'm principled. And of how I like things in the bed. Oh,
where's this?
no. My heart's like an ocean.
Yeah, it's on here.
It's deep and it's open.
I go to the pin out of this.
One thing I promise, I always be honest. Eternal devotion. If we keep things
Okay.
open, if you love all on me,
Clock.
then you let me be free. Yeah.
It's 13.
If you love me, then you let me be free. If you love me,
Okay. Clock signals in.
yeah. I noticed you're driven by jealousy. But my soul is nothing you own. No. I wanna see
Master out, slave in. So data out, which in our case is data into the pin.
no,
we're gonna do pin 1. And then this will go to PA7, which is D11. Okay. Then we have our select pin, which they used PD14, which is D10. And that one goes into the load pin. Pin 12, bottom left. Okay. So these are data in, clock, and you can see here. Their microcontroller, MOSI, IO, which is the CS pin, and then the clock to the clock, which matches here. We have 2 pins here, and we have a clock here. Okay. I think it's all wired up. So if something goes terribly wrong, it's going to happen as soon as I flip this 5 switch on, because something shorted or something like that. Here we go. Oh, let me full screen this. Second cam. Okay. 3, 2, 1. Watch for this magic smoke down here. 3, 2, 1. Oh, to me, that looks like a on display. Is that coming up on stream okay? That looks like it has power if you ask me. I like that. I like that a lot. Let's go. There's no code on it, so this is just the pure power going through it. But that's alright. That's okay. Intensity. So if I put this code on right now, let's see. I think we can just go. We can just make it work. So I'm gonna switch to the code screen, and I don't really know what the test does anymore, because I thought this is what the test was gonna do. I thought it was just gonna turn on the lights exactly like you see. But yeah, we'll see. We'll see what happens. So we're gonna change the dev screen. I'm going to do a run. I also made the intensity to 1, because I figured that it would be better to see if when we put code on it that it gets dimmer. All right. Oh, before I do that, I just realized ground is floating. We need to ground our device. Okay. They share a common ground now. Cool. We're going to program it. Okay, so we get a panic. You're trying to reach a frequency higher than the clock. That makes sense because by default... Oh wait, did I return this? Did I... By default, I think we set our system clock to be like much slower. Where is it? It is in this file. We set our system clock to be this value, which we want it to be enough to run 10 megahertz at least. Or what we could do is decrease the frequency. Oh, maybe we do that. Let's try that first. Let's try to make this, what are we running at? We're running at 32 kilohertz. So we're going to do it at 10 hertz, 10 kilohertz, sorry. 10 kilohertz. Let's see how that may change it. Okay, we didn't get that error. We didn't get that error, so that's good. Do we get a trace back? Logger format contains timestamp, but no timestamp implementation was provided. Okay. Also, I just realized my music stopped. That means I hit the end of the music. The intensity didn't really look like it changed, if I'm being honest. So I don't really think this is using my code. I'm going to try like they do in the example and see if I can just write one value. If not, then I'm going to need to do some further investigation. They wrote a string. I don't know about that. What kind of writes can I do? Display dot write x. Let's try that. Oh, 0. And the value is a byte, I would argue. So let's do 1 1. Does that work? Or does it need to be 1 1 1? Unwrap. Right, hex 32. Oh, 1 1 1. Okay, we'll do that. Okay, let's try to recompile and program. Okay, yeah, it's the same. It is the same, so I'm gonna need to look into that. I will be right back. I just need to handle something real quick. So I'm going to play some music and throw on the BRB screen.
sweet and caring, no cold and calculated. You can't be trusted. You want the world for your own. You want maximum profit. I can't afford to stay, so get out of my way. Smoking down the track, I never looking back. You can't be with me anymore. You can't be with me. Once I will let you in, but now I let you go. I can't afford to stay, so get out of my way. Smoking down the track, I never looking back. You can't be with me anymore. You can't be with me.
Okay. Not sure what will be the sauce to fix this, but I think, unfortunately, I'm gonna have to solve this next time, next stream on Thursday at 8:30. I know this is a cliffhanger, but we did get some serious progress. We at least hooked this up somewhat correct. The circuitry is giving power to this, and oh, hold on, wait a second. Let me just see if we're actually clocking it. I'm curious what our clock speed is. One curious point before I end the stream. We're gonna go to our waveform generator, and we're gonna set up. The system. Oh, actually, we could just watch all three. We could just watch all three. Let's watch all three. I just realized we can do that. SPI. Let's do signals 1, 2, and 3. Okay, 1, 2, and 3. Let me grab these little guys. Oh, I just realized the circuit's not showing. We grab these little guys and hook them in. Okay, sorry. It took a little bit some focused wiring because there's not a lot of space. But basically, I hooked up my digital analyzer to be on the pins. Oh, good. They're all low. Okay. Well, that answers that question. There's nothing coming out of the pins. So of course, nothing's changed. So that means we aren't actually, you know, writing out like we think we are, which means it's a code error. That's okay. It can be a code error. Because of this tool, we were able to deduce that we're not getting anything out of our MCU at all. No data. Otherwise, you'd see ups and downs, especially on the clock. The clock, at least. Which, if you were to look at the code, I mean, I did create. What are we looking for? I created a clock. Or did I? It's past a pin. I didn't actually do anything to it. I didn't configure this to be SPI. It's just a pin. I'm pretty sure that's what's missing. Is that this... There needs to be a step before that does something like this. Where I configure the pin as SPI. Even though this library suggests that you could just do this and it would create it as SPI. Yeah, I'm not too sure actually then. Set low. Maybe it needs to start as high. And then you'd come in here. Do CS dot set low. And set high again at the end of it. Something like that. I doubt it's gonna work, but still gonna put it in there. CS needs to be mutable so that way you can do those. That makes sense. Yeah, if you're gonna be writing values, it needs to be mutable. Okay, yeah, it's the same. Circuit, it didn't change at all. Just fine. And in terms of our waveform, it... Oh, okay, hold on. One of the pins is set to high. The other two are low. Let's label these so at least I can see what it is next time I start the stream up. And then we'll be able to start debugging straight from here. Really quick. We need to see... Oh, it's on here actually. So, PA5, which is D13. D13 would be this blue one. The blue one is going to the green wire on the waveform. Thank you for the follow, Moroider. Is that how you say your name, by the way? Thanks for all the help. I appreciated the Rust expertise. Even if you don't consider yourself an expert, you're more of an expert than I am, and it definitely helped quite a bit. Okay, this one. This one is the clock. Is that what I did? Yeah, this one's the clock. Orange is going to purple. So purple is the miso. And then that leaves this 0 to be our chip select. Which match up, yeah. Okay, so our chip select is being held high. Roughly right. Roughly. Moroider. Moroider? I feel like that's gotta be it. If not, a nice pneumatic explanation would be quite appropriate. But anyways, we're seeing that we're at least setting CS high. We're writing high to it because it's showing high on our waveform. So at least this code right here is working. It's setting high here. Yeah. But okay. Yeah, next time we'll try and debug this and we'll get hopefully this to be responsive using this framework, and then we kind of are just like gonna keep rolling. You know, our goal is to use the DAC so we can actually make sound come out of this thing, which that will be interesting. I'll need to figure out a way to make it so the sound can go to the stream. Because if I could do that, that would be pretty legit. I think I have enough inputs going into my mixer, so I probably could use the audio jack that I'm going to put and run a wire from here all the way to the mixer. And hopefully it's not like, you know, ear destroying. Hopefully. But that would be cool. That would be a cool moment. But we got work to do before we get there. Anyways, thank you for watching, everybody. Thanks for seeing this. This is actually a huge milestone for the Rust development. 0 to FF has begun. We are on index 1 now. Or at least the next stream will be index 1. We just finished index 0. Anyways, yep. Thanks for watching.